Hello everybody. My name is Avi, and I'm the Technical Marketing Manager in Mellanox Technologies. I'm very happy to be in Budapest today. We start with a question. Who here is familiar with Mellanox? Okay, so it's good that I came. Great. So 2 words about Mellanox. Mellanox is a networking company, around 3,000 people worldwide. If people are familiar with Mellanox, usually they are familiar with Mellanox as part of the HPC, high performance computing, mainly around InfiniBand. Mainly because Mellanox is kind of dominating this market, something like 80% of this market. Why I'm mentioning that? Because this is basically the DNA of the company. So the DNA of the company is working with customers like NASA, research universities, CERN, other ones, building supercomputers. And from their perspective, networking should be very simple. It should not lose packets. It should be high bandwidth. It should be very low latency. Basic stuff in that world. In the Ethernet world, it's not so trivial. And basically what Mellanox is doing is taking those capabilities and shifting them to the Ethernet industry. So today, what I'm going to do, I'm going to talk about those features of accelerations and offloads. And let's say that if there are 100% features, 100% are implemented with OpenStack. When we are moving to different clouds, Hyper-V, VMware, it's been reduced, 80%, 70%. So all the features that we are actually providing usually starts with the OpenStack. What is our motivation? So this is a very marketing slide, I know, nice figures, but I don't think you need to see it. Basically everybody knows it, right? We're using our cell phones, taking pictures, uploading everything. There is a lot of data. I think one interesting item is this one. 90% of the data was actually created in the last 2 years. So it means that we are talking about a growth rate which is exponential. And this is the biggest problem. Now, we have a lot of data. The storage is becoming much, much faster. The network is becoming a bottleneck. And this is one of our motivations. The other motivation is the cloud. We are moving to cloud, to what we call software-defined networking or scale out. Scale out basically means that the traffic is moving now east-west instead of north-south. And that's a big difference. That means that the links between the top of rack or leaf to the aggregation level, 10 gig is not enough there anymore. You need more and more bandwidth. So this is another motivation for Mellanox. And at the end, I will show some features, not all of them, of course. I will show some of them. The problem with high-end technology, high-end network, is it comes with complexity. So how we can solve that? Basic ideas like putting everything upstream, make it an inbox, and of course automation. One slide a bit about OPEX, CAPEX, or about that, but of course it's an important part. How we can reduce costs. So the idea is to reduce cost with unique building blocks, and I will touch this later, with what we call open Ethernet, basically opening all the APIs, not locking anything, and increase efficiency. If we increase efficiency, we are lowering costs. So let's start. This is a slide of only the Ethernet portfolio of Mellanox, and basically what it shows is Mellanox is actually the only company today in the world that is doing end-to-end. What does it mean end-to-end? We're doing all the components between PCI to PCI. We're doing the NICs, we're doing the cables, we're doing the switches. Again, cables, NICs, PCI to PCI. More than that, every component that you choose here, we're doing everything also. It means that if you're taking the switch, for example, we're doing the actual silicon. Mellanox actually started as a silicon company. Okay, so we're doing the silicon itself, we're doing the system, and we're doing the software on top of it. And we're actually also doing the software that is managing the fabric. So why do you care about that? You don't. Everything is open. You can choose whatever you want if you are building your network. But the idea is that since we are the only company that actually is doing everything, we actually have some kind of a vision or some kind of a view about what is the purpose of each component in the network. And this is quite unique. Not many companies can say that. For example, we think that all the offloads and accelerations should happen here on the NIC side. And we'll touch this in more in details later. What is the purpose, by the way, of the physical, the switches? It should be a good switch. Okay? And we talk about what exactly is good switch. And it's not so trivial, by the way. So this is just a portfolio of Mellanox when it comes to switches. Those are kind of known in the industry. Aggregation level, 32 ports of 100 or 40. And this is 48 ports of 25 or 10, which with 8 uplinks of 100 or 40. Everything is okay. This one is unique. As an example, how unique building blocks can help when it comes to cost and performance and other stuff. This is basically 16 ports of 100 gigabit in 1/2 19 inch. It's half a space. So if you're putting two side by side, basically you can actually operate 40 servers. And there is a nice use case which I can show you offline afterwards. 40 servers connected and still be non-blocking in this size. And you're putting two side by sides, so basically you have full high availability. And everything basically you should have, you are getting from this side. This is 125 watts per device and 300 nanoseconds latency for all the switches. What's running on top of the switch? So this is about the physical network. Open Ethernet basically means that the product can actually have several operating systems running on top of it. So it can be Mellanox OS, which is our operating system. It can be SnapRoute, Sonic from Microsoft, OpenSwitch maybe later. Cumulus Linux, which is a very interesting operating system. You're familiar with Cumulus? You heard about it? Okay. So we'll talk about Cumulus Linux. I'm just saying Linux, so it basically explains what it is. Basically, it's Linux on top of a switch. It's a Debian Jessie basically running on top of a switch. And it means a lot in an OpenStack environment. And what exactly, how does it work? So basically, every operating system needs two things. One of them is a way to upload itself into the device. And then you need something like Oni, which is kind of a PXE boot for switch devices. Or actual PXE for some cases. And another thing is that this operating system needs to actually talk to the silicon that is running. And the way to do that is via what we call Switch SDK, which is the API for the silicon to control the silicon, or something that is called SI, which is actually standardization of all SDKs, almost all SDK in the industry. The most significant ones are Mellanox One, Mellanox Spectrum SDK, and also Broadcom, of course, which dominates the market today when it comes to silicons. So for example, Microsoft Sonic is running over SI. From their perspective, they can just shift and replace the hardware as much as they want because the application is running over SI. They then don't care what exactly is running beneath. A word about Cumulus Linux. So I think that today saying that someone is buying servers as a blob that contains the hardware and the software that the vendor decided, the features that the vendor decided, sounds kind of a crazy idea, right? Everybody is buying the hardware that he wants, uploading the software that he wants, and so on. And this is exactly what's going on in the network industry. In the network industry, the same trend is happening now. Okay, it's not something in the future. No, it's actually happening now. And basically today you can buy hardware that you choose and putting the operating system that you want and actually running the application that you want over the switch. And Linux is a great operating system. We know that, right? So having Linux on a switch means a lot. It means basically you can use Ansible playbooks to automate your switch with the same modules that you're actually using on the server side. It doesn't have to be Ansible, it can be Puppet or other tools, SaltStack. But anyway, once you have Linux, you have a lot of options on the switch. And here is a more advanced idea even than Cumulus Linux. Cumulus Linux is still a license. Here I'm talking about something that's called SwitchDev, something that Mellanox is pushing and developing in the community. It's basically a simple driver for a switch. It means that if you like to just go upstream, Fedora, install operating system, Red Hat, whatever you want, and you just need to install a driver, and that's it. Like you are doing on the server, right? If you have a NIC, you're putting the NIC, you are installing a driver, that's it. So I have config, you have two interfaces, great. Same thing here. You are taking a switch, putting with Pixie the distribution that you would like to put there, installing the driver, the switch dev, and that's it. You are seeing 32 ports. And you can use the IP utilities, and you have hardware monitoring, CCTL, and other stuff. Okay, everything is already there. This is a product that is currently, it's a GA, but a limited feature set, but it's growing. Okay. And at the end, we need also the physical network, the switches, to run some protocols related to overlay and other things that you need to put there. And that's great. How you can differentiate between different vendors. So the features, well, they are there, and there are differences when it comes to scale. But at the end, the power is actually on the silicon itself. So the silicon itself, this is actually the switch. This is the fast path. This is how traffic is moving. And this is something that's called total report. I'm not getting into that too much, but it's just a comparison between Broadcom, which again dominates the market, Tomahawk, with Spectrum. And if you remember at the beginning, I said that we came from the HPC market. So for example, Spectrum is not losing packets in any packet size, while Broadcom does lose packets. So why people are not seeing it? Because they are running TCP/IP, there is retransmission, on the application level you don't see it, but still on the physical level there are packet loss. Latency, of course, is the lowest in the market, and there is a nice graph here about the buffers, which I will not touch currently, where we are providing fair buffer capabilities on the switch side. This is about the physical network, the switches. So we have Linux on the switch, great. Looks nice, we have the features and everything. I mentioned at the beginning, all the offloads acceleration are actually happening on the NIC side. Our NIC is called ConnectX. There are different generations. Started with ConnectX, then ConnectX 2, 3, 4. We are at 5 actually right now. This is a fan of the different capabilities that we are offering with the NIC. I will touch today actually 2.5 of them. One is called RDMA or Rocky, and the other one is VXLAN offload and OVS offload. So yeah, so those are the items that I will touch today. As I said, it's a portion of the offloads that we're offering, and those are the ones that I'm going to discuss today. One thing I want to say about high-end network or network that is running 100 gigabit, 25 gigabit, 50 gigabit. If I would go and deploy 100 gigabit network and plug it in and try to get 100 gigabit performance, probably would not happen. And I will show some examples here, because there are some boundaries from the server side, from the application side. They can be solvable with more CPU power. So if I was an Intel guy here, I would probably tell you, okay, you should go DPDK, you should use more CPU because I want to sell more CPU. But the idea of Mellanox is, first of all, we are sending NIC cards, network devices, and we think that the network operations should be handled by the network, by the NIC, and not by the CPU. And this is the main idea, remember that, when we are speaking now about those different offloads. Let's start with Rocky. So what exactly is Rocky? Rocky is RDMA over Converged Ethernet. The idea is very simple. Everybody here is familiar with TCP/IP, right? I don't need to speak about that. It's a transport protocol, started at the beginning of the Ethernet world, and that's the problem, because it tried to evolve and try to keep up with the rhythm of Ethernet, but it started back then. So it has its limitations. Its biggest limitation is that this TCP/IP is basically when you are copying data from one server to another server, moving memory from one to another server, you need to go through the software. You need to go through the protocol stack. So you are involving the CPU. Now, this is the biggest problem with TCP/IP. For network operation, basically you get high CPU utilization. And the idea with Rocky is basically saying, no, if you want to copy a memory from one server to another, you don't need that. You can just go directly from the application to your NIC card. How exactly does it work? It works basically in the way that we are creating shared queues between the shared queues between the application itself. They are called queue pairs or QPs, send receive. And the NIC card has capabilities inside, hardware capabilities, where it actually has the mapping table between the virtual memory addresses and the physical ones. So once they are connecting this application, the NIC card, once there's kind of a handshake between those two, the NIC cards have direct access, and of course it's all secured and segregated to the memory, and it can actually go and copy the buffer directly from the application to the other side. So this is why, for example, I can show some videos where we're actually running 100 gigabit between two servers with 0% CPU, because the CPU is not involved anymore. We're just copying the data from one server to another. So this is the idea of Rocky. If I remember right the details, I think we can reach up to 170 million packets per second with RDMA today. That's nice, but this is more kind of for bare metal server. What's happening in the virtual environment? So somehow we basically need to get this virtual machine direct access to the E-switch, which is kind of the V-switch on the NIC side, the hardware implementation. So how exactly we're going to do that? So let's go back, history back, and talk about a NIC that was called E1000, Intel one. And basically it started then, when what they said is basically we're going to create a mock of the device itself into the virtual machine, a full software implementation of the device into the VM. So the good part is that you don't need special drivers for it. Those are the same drivers. The bad part is that on performance side, it's very slow. The software is very, very involved, and it's very slow. And then we move to something that is called power virtualization, which basically means that we are moving and creating actually a virtual device on the VM with its own driver. And most of the operation is happening on the hypervisor itself. So the performance was much, much better, but still not close to what we are looking for when you're using Rocky. And there was another idea, basically taking the physical device and giving the VM direct access to the port. But at the end, you have 2 ports, 4 ports on the servers, that's it. So what, you have 4 VMs, it's not really scalable. So the way to go at the end is something that is called SROV, which is single root I/O virtualization. And the idea there is basically taking what we call physical function, which is the function that is controlling the actual port, the device itself, and copy it. So we can copy it actually up to 256 copies of this same physical function, the same port, and creating something that is called virtual functions. And now we can have different VMs connected, each one to its own virtual function. From his perspective, it's kind of like the actual device. And now we have actually a direct access from the VM itself to the NIC card. And then we can actually implement the Rocky, as we described earlier. So this is about the SROV. And actually, SROV is something that is available actually from Icehouse as a proprietary mechanism driver. And from June, it's upstream. It's called SROV something, I don't remember the name exactly, but it's there. And you can see some numbers here. It actually gets the same results as a bare metal when it comes to latency and bandwidth. The thing is with Rocky, there are challenges with that. And the big challenge with Rocky is that you need to implement your application in the way that it's talking Rocky. It's using Rocky API. So there are different ways to do that. The most complicated one is called verbs. I will not get into that, but it's actually an API that creates this handshake and connect directly to the PCI and so on. The other option is to use libraries, which are basically working on top of the RDMA API, but provide a socket API. From the application perspective, it looks kind of the same. But there will always be some kind of an effort working, and customers are doing that, but actually developing applications that are running over RDMA. The places where we can actually gain from RDMA or Rocky for free is actually the storage space. And why is that? Because there are other people that actually already did it for us. They build the storage application on top of RDMA. One example is ICER, which is iSCSI over RDMA. It's an open iSCSI, and it's already available for Havana. And you can see some numbers here. You can basically, with this option, get 5 times lower latency and 6 times more bandwidth. More important, very low CPU utilization. So you can see some numbers here. The thing is that with HIOP, kind of a thumb rule say that if you are reducing the CPU from the network, you will get more IOPS. And the idea is very simple. If you are reducing CPU from the network, it means you have more CPU for your storage. So this is ICER. And actually, the configuration is very, very easy. I didn't mention it here, but a couple of lines, Nova and Neutron, and you have it installed. The most popular one is probably Ceph. So Ceph is a great thing. The challenge with Ceph is that on the network, it creates basically more data, control data, right? So there are the data replication and the self-healing and self-monitoring and other data that is running for controlling. And one thing I can say about that is, first of all, many customers are using dual ports, 2 10 gigabit. To do that, my recommendation will be why 2 10 gigabit if you can have 125, which is more than 2 double 10. We actually recommend on 50. Okay, so we'll not get into the network design recommendation right now, but bandwidth is something that is definitely helpful when you're coming to work with Ceph. But more than that, we are actually working together with XSky, Samsung, and SanDisk about Rocky over RDMA, Rocky over Ceph over Rocky. And today in the POC level, we actually can show, there are some demos in the internet, you can see them, really high performance with Ceph over Rocky. And it's really, actually 2 lines in ceph.conf, and you actually enable it. So basically you download Ceph and you are changing the configuration on ceph.conf and you have it ready. And the idea is, again, simple. Once Ceph is working now over Rocky, all those control packets, all this extra overhead network is being done without CPU utilization, CPU usage. And there are wikis and community links that are available for that also. The last storage item that I would like to touch is NVMe over Fabric. So what is NVMe? NVMe basically is a way to accelerate the storage, just bypass traditional or legacy connectors that are not really relevant for high performance storage. And this is NVMe. So what is NVMe over Fabric? NVMe over Fabric is doing basically continuing this notion and doing it between nodes over the network. So it supports range of storage networking fabrics, but definitely the leading one is Rocky. And why is that? Again, the idea is the same. Since we are on the local servers, we are bypassing old connectors. In RDMA for the network, we are bypassing the TCP stack and basically moving the memory directly from the application, storage application, over network without CPU involvement. And around this activity, we actually have a blueprint in Cinder, but looking forward, we're looking at Pike and Queens for full implementation. Just number about NVMe over Fabric, which is interesting and can give you some idea about where we are going with storage and how it affects the network. So to utilize 100 gigabit with spinning disk, you will need something like 250 spinning disk. But to do the same with NVMe, you need only 4. So once you have 4 NVMEs, you have a problem because now 1 gigabit is not enough anymore. And this is how we advanced from HDDs to NVMe. Actually, there is an even faster now solution, which is called 3x solution, but you can see the difference. And also from the latency perspective, and this is also interesting. At the time, the thing is, the disk latency was so high that even the application, even the software was low than that. So it doesn't matter too much if you have 6,000 microseconds latency and the software is 200 microseconds and the network adds another, I don't know, 100 microseconds, it doesn't matter. But now what's happening is that on the storage, the storage itself is bringing something like 20 microseconds. And the software is also 20 microseconds. And now the problem is that if you're adding only just 1 microsecond, that's it. The network is just shifting now the latency problem into the software plus network side. So this was about Rocky. And now we would like to touch also overlay. So what exactly is overlay? I don't think I need to explain it too much here in this room. In 2 words, basically, is the way to continue to have layer 2 fabric, but with scale. How it can be achieved? Basically, we have an underlay, which is usually IP fabric, and we are riding on top of it with overlay, which is VXLAN. And that way we can achieve a scale, move from basically VLAN, which is limited in scale, layer 2 fabric into a large layer 3 fabric, scale out, leaf spine, and so on, but still keep the layer 2 notion. So that's great. You can do, VXLAN termination. And what exactly is termination? Okay, so termination basically is you need to some way in the flow basically to terminate the VXLAN and move to VLAN. It's called encapsulation and decapsulation of the packet. It can be done on the top of rack side, okay, and this is being done mostly for bare metal, different protocols like a controller that can do that, or EVPN. And also another option is to terminate over on the hypervisor. But people sometimes forget something about VXLAN, so I would like to remind us all about this. VXLAN at the end, it's a UDP packet. It is what it is. It's a UDP packet. And the thing is, from the NIC perspective, if I'm a legacy NIC, for example, I'm getting hit with a traditional packet, Ethernet packet, with a VLAN, I know what to do with it. I'm going, I'm checking, I'm doing the checksum, and I'm probing the header and doing the RSS TSS, so I will have good load balance, okay, between the cores. But if I'm getting hit with a VXLAN packet, I have no idea what to do with it. It's just UDP packet, okay? So what I'm going to do with it, I'm going to push it up to the software. And the software will do the job for me, okay? It will go and probe the inner headers and do the checksums and the RSS TSS and other operations. That's not good, because again, if I'm involving software in a network operation in 100 gigabit, even 25, sometimes even 10, I'm creating a problem. The software cannot cope with that. So for the software to cope with that, you need more CPU power, and this is exactly what, as I said, we don't want to do. We want to leave the network operation for the network. So what we did is basically took this VXLAN capabilities and put it on the NIC side. So basically, with a NIC that provides VXLAN offload, you can actually have those operations, the checksum, RSS, TSS, being done by the NIC. And then the NIC, again, is doing what it's supposed to be. Okay? It's going to the inner header, probing it, and doing those operations. How exactly you are operating this feature, it's just there. If you are putting a Mellanox card, you need to, of course, configure the driver. There is one configuration that needs to be done there. There's a committee to describe that. And that's it. From now on, when you are running VTAP on the hypervisor, the VXLAN offloads is being done on the NIC side. So this is one feature regarding overlay. And you can see here some numbers about overlay. So you can see that this is with VXLAN offload, and this is just bare metal, physical VLAN, and the performance is the same. If you are not using offload, the performance reduced, but the bandwidth is reduced, and also this line is showing the CPU. Okay, to overcome this operation of the VXLAN, which is RSS, DSM, and checksum, you need CPU to do that. So there is more CPU power needed for that. OVS offload. Well, everybody knows here about OVS. The idea is the same. So we mentioned SROV, right? In the context of Rocky, how we can get actually direct access from the VM to the NIC card, which is nice. But once you are bypassing the hypervisor, you are bypassing all the functionality that hypervisor actually provides. So that's a problem. One of them is the OVS. So if you have policies there, for example, in normal condition, you will go to the hypervisor, the hit will be on the user space and then on the kernel space. What we did basically, we said, okay, now we're going to move the functionality also to the E-switch, to the actual NIC. So the OVS is running there. It's called A sub square or OVS offloads. A sub square is the marketing term. But basically now the rules are sitting here on the E-switch. There are two ways to handle it. One of them is saying, okay, run with SROV, basically have direct access to your NIC. So you need 100% functionality of OVS on the NIC side. This is almost impossible. Everything is evolving. So there are people that are doing that, that's fine. But there is also a flex option where basically for the rules that you have on the E-switch, use the E-switch. If you don't have them, you're just going back to the normal operation. So in that way, basically, it's a great feature, but you can be flexible and actually use it when you need it. So those were regarding offloads and accelerations. And now I would like to talk a bit about control plane. So each network vendor comes with some kind of a tool. So we call it Neo, Arista we call it CloudVision. There are other tools around there. Neo, on Mellanox perspective, is basically a tool that is managing, and this is what differentiates it from other tools. It's managing different operating system. It's part of the Open Ethernet idea. So it can manage Mellanox OS or Cumulus from its perspective. It doesn't care. Showing us graphs, GUI, monitoring, provisioning, everything is there. Basically, it's running over REST API. So if someone needs to integrate it into its own system, it can do that. But since it's running over REST API, it was also very easy to actually integrate it into Horizon. So from Liberty, you can launch Neo from Horizon. Except of the monitoring provisioning of Neo, there are some network operations that needs to be done, and having kind of a fabric manager that can connect and do those things is very important. So one of them is having the Mellanox ML2 driver, mechanism driver, talking with Neo and creating VLANs, to do fabric provisioning, creating VLANs to create networks on the physical network. Another thing that we did is we work with Ironic, and basically with Ironic there is an issue where you need to move from the provisioning network to the tenant network. So basically there is a simple flow when you need to move from one VLAN to another, and this is again being done by Neo. Neo, by the way, is a free software. There is no license, not anything. Just it's free free of charge, and this is about Ironic. And we are currently working at the POC level also about a scheduler that will take under considerations also the physical network aspects. It means that if you are spawning a new VM, Neo can actually recommend different recommendation about the network itself. For example, if the VM needs to run on a physical server that is part of some kind of high availability, 2 top of racks or not, bandwidth requirements, and so on. So Neo can do that, and this is also part of Okata. Just to summarize what we discussed till now, so at the end, as I said, there are many, many features. We talked about part of them: Rocky, overlay, control management, integrations, and so on. The idea is just putting them in box. Okay, so it touches different projects. It can be Cinder, Nova, Neutron. The functionality it's right there. We just need to actually activate it if it can be a configuration file or a configuration file of a driver or the actual process. And beside of that, and I didn't touch it, there are, of course, we're working together with big distributions. And most of the features that actually I described today are also implemented with InfiniBand, which is less common, but you know. At the end, it's about a solution, right? So the solution means that you can have the flexibility to choose where you are doing the VTAP, for example, if you want to do it on the hypervisor or on the top of rack. And which controller will you use? Are you using neutral, or actually are working with one of the controller vendors? Or maybe BGP VPN, and use unique building blocks like the 2100, when you can put two side by side, they have full functionality, full requirements fulfillment with this size, with lower power and so on, and have the aggregation level that you want, and running Linux on a switch if you like, and choose the automation tool that you are using today also for the switch side. I didn't even touch the container aspect, but think about it, Linux containers, you know, just an idea. And at the end, this is the full solution, and once you are choosing your design, you can actually activate the features that you would like to activate on the storage side or on the overlay side, and have those ability in box. And this is a real use case. It's a company called Sys11. I just picked one. Sys11 Germany. It's a hosting company, and it's using the products, and it's actually using almost all the features that I described here today. So they are running Cumulus Linux on all the switches, Ansible to automate. They chose Midonet for the controller, running Itaka at the time at least, and VXLAN offload is activated all over the NIC card, so it's coming for them by default, and they're going to use OVS offload soon. The interesting thing about Sys11 is that Cumulus actually certified Quagga as the protocol stack. Okay. Today, the Quagga name is a bit different. I don't remember the exact name. It's called free range routing, something like that. But it was Quagga at the time. But the customer came and said, no, I would like actually to run layer 3 from the aggregation down to the server side. I actually want to run protocol stack here on the server side. And what I would like to run there is Bird. So Bird is just another protocol stack. So I would like to run Bird also on the switch side. And we said, okay, that cannot work, right? Because Quagga is a certified protocol stack. So he came and said, wait a minute. You told me it's Linux on a switch. If it's Linux, then I can choose whatever I want. I'm not asking myself if I can run Quagga on the server or Bird. I will choose whatever I want. If this is Linux on the switch, I expect it to be the same. So we were a bit concerned, but he actually did it. He actually ran the first time, I think the first customer that ran Bird on the switch, and it worked. And this is actually the power of Linux on the switch. It just worked. Immediately on the POC level, there were 32,000 routes, and now he's running over 100 routes with Bird on the switch. And this is actually an OpenStack cloud deployment, public cloud, that is running up and live right now. 25, 100 gigabit, 25 to the servers and 100 gigabit between top of rack and aggregation level. Thank you very much. If you have any questions.
Yeah. So my first question is whether the advantage that you show here is because of the direct NIC access and bypassing the kernel, or because of the transport network? So because it seems that you rely on the fact that you have no packet loss.
Right. Okay, that's a great question. So yes, so I mentioned Rocky, right? Bypassing the kernel and moving between NIC cards, and that's true because think about it, if you're not using TCP/IP, you don't have retransmissions. So somehow we need to make sure that you're not losing packets. So a good thing is that Spectrum switches are not losing packets. It's a good start, but it's not enough because there can be congestion points, right? And then you can lose packets. So there are different ways to do that. Let's say if you want the best performance, you will need to run something like PFC or global pause, basically flow control, to make sure that packets will not be dropped. This is one option. But usually, it's very difficult to do that. There are network requirements, and it's a bit difficult to do that. There are people that are doing it, but it's pretty difficult. The other option is to use ECN on the edges. So this will always create, this will be called as a lossy network, but still you will not lose packets. Also there is a kind of a challenge. What we are actually recommending is something that's called semi-lossless, where basically we have great capabilities of buffers on the NIC, and we're going to utilize them. So on the network side, on the switch, don't need to do anything, but the NIC side will observe the congestion and will be able to handle it. So today, actually, we are using something that's almost lossy for the network, at least from the switch perspective.
So would it mean that there are scenarios where the Rocky is not the best option? And talking about special features, so if you need to fulfill requirements like traffic shaping or multicast or IGMP, either join read messages. So would it mean that such an Apple scenario, so in these cases, so probably Rocky is not the best option?
Okay, so you can, some of the things that you said can be implemented via Rocky. There is no problem there. But in general, yes, there can be some features that, it's not that you will not be able to implement them, but you need to invest a lot on the application side to do that. Okay? So this is why I said there are challenges in the application layer to actually use the right APIs of Rocky to actually implement it. And the easiest way, as I said, is just go with what already has been done. It's mostly around storage.
Can you run OpenStack neutron on top of the switch with acceleration?
Sorry, guys?
A neutron node on top of that Linux on switch.
On switch.
With acceleration.
I don't think we tried it. Theoretically, probably yes. But the thing is about, I said it's a Debian Jessie over switch, but it's a Debian Jessie with a lot of stripped libraries, because we don't see any need of running those libraries in the network device, right? You can actually add them back, but we don't think it's right to do that, because the switch itself is kind of a critical point in the network, and we don't think that you need to do more, to load the CPU more with such operations. So it's not something that we recommend.
Coming back for a second for the Rocky, if I understand what the Rocky can provide the advantage if both the application uses the Rocky API. So what happens if one application is capable for the Rocky but the other one is traditional TCP/IP? Do you plan to introduce some adapter mechanism at the NIC level which can TCP/IP frame the packet which is coming from the Rocky API, and on the left side we can avoid the kernel process handling, because this is also a reasonable CPU
Yeah.
And on the other side, it will be compatible with the legacy TCP/IP packets.
Yes, so I don't have an accurate regarding OpenStack. I know that in different environments like VMware, we actually implemented it in some scenarios. I also think in Ceph it's the same idea. So basically in theory, not in theory, in practical, we're actually building the design in a way you don't have to actually use Rocky on both sides. The only thing is that if you are not using Rocky on one side, you're probably going to lose the performance aspect, because you are moving back to TCP/IP.
In one side, yes, but if you have several other nodes, for example, if we are talking about a load balancer, the load balancer is Rocky capable, but the worker nodes are not, so those are using TCP. So I still can eliminate the bottleneck on the load balancer side, and the scale of worker nodes can handle the load.
I agree, you can do that.
Okay, sounds good.
Okay. I have two questions actually. One is that you mentioned that you heavily invested into offloading the VXLAN handling. Because in your case when you're doing the VXLAN handling in the rack. So However, even in this case, we are using the VXLAN, so we are actually adding quite some additional headers on top of the original payload. I wonder, for example, especially in case of this reference customer who is using only your gear, do you have a solution which would, let's say, eliminate the need of VXLAN and put a lot of overhead on top of those packets?
So no VXLAN.
No VXLAN.
Okay. So
I'm just curious.
no, that's a fair question. So there are companies like Humulus, for example, that are actually recommending to do layer 3, only layer 3, okay, till the server side, especially, by the way, when you are running with containers. And then just to avoid all the VXLAN thing. Actually, the idea of VXLAN, the rumor, and actually I think it's a true rumor, was invested by server guys, not the network guys, right? Because the server guys wanted to just have the, their old layer 2 connectivity. They want to create a VLAN and connect. That's it. And with layer 3, it's much more complicated to do that. So yeah. So we can also say, look, you can run layer 3 to the server side, and just have the scale that you want with layer 3. You don't need VXLAN, not need anything. But still, there are some restraints, and sometimes you need to run VXLAN. For example, you have a legacy layer 2 data center. You want a data center interconnect. There are several scenarios. You need to scale, but still have layer 2 functionality. Then there is no other way.
Yeah, for those kind of cases, I was really in these kind of greenfield situations. And the other one was, how is the addressing done in case of the rookie solution? So, is there some sort of mapping? Basically, on this IP level, you have the 5 tuple, which identifies the socket. So how is that going on, and how is that, if it needs to be somehow interlinked with, newly provisioned virtual machines, so how is discovery working as such?
So with Rocky, actually, you can do it two ways. You can still stick with the traditional IP and everything, but there is also another option to work with what we call verbs, which is actually some terms that are coming from the Infiniment. I'm not an expert in that, but basically they are kind of equivalent to VLAN, and yeah, it's the same. It's actually the same idea, but I'm not really familiar with.
But then you need to somehow tell the application running in one virtual machine some kind of ID of the other virtual machine. I suppose is that.
This is the case, yes.
Okay, and that somehow you need to sync them with the.
It doesn't, it's think about it, it's a layer that doesn't interfere with a regular network operation that you are used to with Ethernet. Okay.
Okay. I don't know if there are any questions. If not, then I think thank you very much.
Thank you very much.